Welcome to the first episode of Putting the Audience to Deep Sleep, where we are going to go into deep system design. In this episode, we will cover a variant of Ticketmaster problem. If you find this video useful, or if the video helps you get a power nap for next 15 minutes, please subscribe to our channel. If you're still awake at the end, then definitely subscribe to our channel. I have linked the transcript and the final generated summary in the description. Unlike most things in life, the requirements of a Ticketmaster style problems are pretty straightforward. User picks a quantity, buys the ticket, and the main challenge is avoiding double bookings and making sure the order goes through correctly so Ticketmaster can pay their bills. But what if we tweak the requirements a bit? What if instead of just buy 3 tickets, we need to support booking specific seats with specific tiers at specific prices per event? The double booking problem doesn't go away, but this dramatically changes how our schema needs to be designed. In this problem, this is exactly what we are going to look into. If you're an interviewer, please refrain from getting any ideas from this video. Let's take a look at the existing system. We have the usual setup of an API gateway routing to an event service, which has a caching layer and talks to the events and bookings database. There is also a search service with its own database and some sync between the two, presumably to keep the booking and event data in sync. Quick note before we start. You'll see something called JIT context in this video. It stands for just in time. It's a small hint box that pops up at the beginning and again if you get stuck, to give you a few thinking points without giving away the full solution. Like in this problem, we start with simple Ticketmaster style schema. The JIT context nudges you towards the key design decision. What a seat is as an entity, what belongs to the venue versus the event, and which tables you need to support seat map tiers and event specific pricing. Now let's check out what the functional and the non-functional requirements are for this particular problem. On the functional side, we want the ability to see a seat map with availability, support tiered pricing, and let users pick specific seats. On the non-functional side, venue can go from 100 to 80,000 and we need to handle multiple events at the same venue. Next, I want to see what the existing schema is. In general, I think it's best to build upon something that already exists rather than rewriting from scratch. So here we can see that we have 4 tables: events, venue, orders, and users. The events table has a flat remaining tickets count and a single cost field. The venue table just has a seat count, which is literally just a number. Orders references a user and an event with total quantity and cost. As luck has it, even after 300 interviews, I have never got anything this simple. The schema has no concept of which specific seats are booked or tiers for events. The cost on events is one value, so every ticket to the same event costs the same, and remaining tickets is just a counter that just gets probably decremented on purchase. This works fine for general admissions, standing room concerts, unreserved festival seatings, or random company happy hours and recruiting events. It's simple and fast. The model would, however, not be extensible for the functional requirements that we have. This is because a single cost can't express VIP is 3 times more than standard tickets. Remaining tickets don't really tell you which seats are available. We also need to know like a spatial information of row, column, and sections. And the order table tracks quantity but can't specifically tell you which seats belong to that order. So let's write down the schema first, and then I can walk you through each of the decision points. Let me copy this onto the scratchpad so that we can see how the current schema looks like. Grab your coffee, this is gonna get dense. Here is the schema I have. So we have seat venue config to map each physical seat to a venue and its row, column, and tier. Tier config is to define tier categories at venue level. I added event tier config to bridge tiers to events and event specific pricing, and seat event booking to track which seats are booked for which events using a composite primary key of SID and EID. I'm trying to separate the venue topology from event. So venue's physical layout doesn't change between Saturday night concert or a Sunday conference. The rows, the columns, the sections, they all remain the same. This is to avoid redundancy and keep tables normalized. Another way could be to have seat definitions into events or booking tables, but that will result in copying the entire venue layout for every single event. There might be venues which might have such options, but for simplicity, I'll keep the venue layout static as that was not in our functional requirements. Pi usually complains about my approaches. Let's see if it agrees this time. So to find what's available, we can do a left join between the seat venue config and the seat event booking and filter for the nulls. Basically saying, show me seats where no booking row exists for this event. Note that this approach is known for making interviewers squint since 1979. Another option could be that when a new event is created, we could just copy all the seats with initial status available and then mark them as booked. But in my mind, that causes redundancy because there may be shows which are not completely booked out, which causes us to create the seats not sold as opposed to the current solution, which I feel is more storage efficient. There are many approaches to this problem. One idea could be that on the UI, we show section styled pagination, like showing sections rather than loading all 80,000 seats at once. Usually, when I go to Ticketmaster, I select the section based on maybe pricing or a range or how close it is to the stage. This reduces the load on the DB to an extent since we are not fetching 80,000 rows, and I also think it's a much better user experience. As I mentioned, I think it's a better approach to only add seats to storage which are booked. Let me see what happens if I try pushing back to Pi. The solution suggested by Pi, which was to add a status field, we could go with that. It will essentially pre-populate an event when it is created. Every seat will get an explicit row from day one. That makes querying much easier because now we can have a direct lookup per event rather than computing availability through joins, which will result in much faster queries. We could also do a cleanup and move them to a different archived storage once the event is over. But I still think we should not have redundant data. I hate it when my manager asks me, why are we paying so much for the DBs? During summer, for example, we have a lot of events and even around holidays. If an event only fills up 50% of 80,000 seat venue, that's 40,000 rows sitting there with the status of available. Rows that purely exist to tell us something we can infer from their absence. This approach keeps the indexes smaller, faster backups, and less replication overhead. The downside is that we have to compute the availability via left join, which adds query complexity and performance overhead depending on how full the event is. That's an interesting question. Um, every Even with indexes, running a left join across 80,000 rows on every seat map request adds up fast when thousands of users are hitting it concurrently. Each request is touching a significant chunk of venue table. The database might handle it fine at low traffic, but not for a hugely popular events. For example, like Super Bowl or Taylor Swift concert. We could reduce this load by having some form of cache, which, by the way, would be required for any of the solutions that we go with. Usually, the availability page is what we want to load the fastest. That's why even today, if you go to Ticketmaster, you don't need to actually log in to view availability page. With caching, we have to accept that there will be some form of eventual consistency, which is the trade-off that we'll have to make. The reason for eventual consistency is like, let's say there are 100 tickets left and cache is reflecting the same. Now, when a ticket is purchased, there is a moment when the cache is still 100 and the DB has decremented to 99, assuming the user only bought one ticket. During this time, the cache will be outdated. At some point, this data will be updated and cache will also go back to 99. We have to be careful where the staleness is. For instance, having some staleness in total ticket count might be okay, but having staleness of availability when the user is selecting seats can lead to a pretty frustrating experience. which is also very consistent with what we all experience on Ticketmaster. This is the actual tricky problem. When an event is created, the cache gets hydrated with full venue layout, all seats marked available. Then, as bookings come in, the cache gets updated incrementally. And this is the trade off we want to let the interviewer know that we are making. One other way I have seen Ticketmaster deal with this is by not showing the total count of the tickets available, but maybe showing a range or just availability like high, medium, or low, which subtly tells you that they are not really sure either. However, our actual booking flow will always have strong consistency. One thing worth calling out though, the cache invalidation strategy here really matters. Some options are write through cache, where we update the cache on every booking synchronously, or write behind, where the updates are batched synchronously. Another option is TTL based expiry, where entries expire and then refresh from database time to time. Each of these have different failure modes and different trade-offs. Write through adds latency to bookings. TTL based means you live with stale data for a bit. For a high throughput ticketing system, write through with a short TTL fallback is usually a sweet spot. In this case, I will go with like write through. The order processing takes time. Adding a simple caching invalidation step will add few milliseconds, but will guarantee stronger consistency than other options. The moment two users compete for the same seat at the same time, we need hard guarantees. This is one of the key topics for every Ticketmaster video that you will find on YouTube. This basically goes to the concept of locking. There are three types of locking mechanisms: pessimistic, optimistic, and distributed. There are other options as well where there is a hybrid locking mechanism. For this, I think I will end up using optimistic locking. We can make sure that when the user clicks on the seat, we put a hold using the locking mechanism and finish order processing. If you want to learn more about locking, or you want to harden your concepts, try out one of the problems we have specific to. We could also be the 1 millionth creator to create a video on it. So the flow will be: the user clicks on the seat, clicks on add to cart, we put a timed lock on the seat row, process the order, and assign seat to the user once the order completes. In case of failure, we roll back, or when the time lock expires, the seat will be released to other users. So thinking a bit more, I think actually I will go with pessimistic locking, which also matches my personality. Usually, pessimistic locking degrades user performance as it puts a lock on the row, which causes other requests on the row to fail. But in this case, we are going to lock the row for a particular seat, and we don't want any other holds on the same row. While optimistic locking will also work, I think pessimistic locking is much simple and it will actually suffice for our requirements. For this, I will add a field called as OID, which would be the foreign key reference to order ID to seat event booking. With this, we can release all the seats in the abandoned cart in a single query. For TTL, we can lean on databases native row expiration functionality. In practice, the implementation depends on different database. For example, Redis, Dynamo, and Cassandra support native TTL. Some DBs don't, like for example, Postgres doesn't natively support TTL, but we can add a timestamp column and run a periodic cleanup using a cron job. Another option, in case primary store does not have this functionality, is a common hybrid approach, is to use Redis for the hold with a TTL and write to relational database only on confirmed booking, keeping the transient hold state in the store optimized for expiration. The status field can help distinguish between a seat that's temporarily reserved during checkout and one that's being paid for. This status can also drive the seat map display. So there you have it, folks. We just practiced one quick Ticketmaster drill on schema design. You can also check out the summary, which includes some highlights on where the interview went well and some tips on where you can hone your skills. The summary is generated after every drill. You can also access the transcript for this problem using the link in the description. If you want to practice any other type of concepts or get a better understanding on the concepts, visit our website on hellopy.ai and pick any problem that you want to practice.